Hello everyone. So we are continuing with the heterocycles. Now we are moving little ahead and we are coming to benzo-fused heterocycles. So benzo-fused, that means heterocycle is there on which benzene is attached. So a lot of examples are there. First we'll see this indole ring, okay. So this indole ring is benzo-fused to pyrrole. It's very important. Now you know pyrrole is very much like benzene, okay, because pyrrole has nitrogen has lone pair, so electrophilic substitution happens as effective or rather better than benzene, right? So when benzene ring is attached to pyrrole, this is called as indole ring, and it's a very important constituent of one of the very famous amino acids, tryptophan, okay. So you have to remember this. You cannot forget indole ring because it keeps coming again and again. So you attach a pyrrole ring on a benzene, it is called as indole ring. So this is amino acid on that it is there, okay. Now interesting thing, before I come to that, let me talk about this pyrrole. So in pyrrole, I told you whenever the electrophilic substitution happens, it happens at position 2, and if position 2 is occupied, then it happens at position 5, so just next to the nitrogen. Why? Because maximum amount of conjugation happens here, okay. It comes here, then it comes here, and that's why it will not happen at position this or this. So it will not happen at position 2, it will not happen at position 4. Electrophilic substitution happens at 2, and if 2 is occupied, then it happens at position 5. But interestingly, indole, it happens at position 3. There is a big difference. Pyrrole, it happens at position 2, and indole, it happens at position 3. Why? Because it's already a benzene ring is attached, and if attack has to happen at position 2, this lone pair has to come from here, then here it comes, then there is a loss of aromaticity of benzene in the process. So it becomes highly unstable activated state, transition state. So it needs huge amount of activation energy, so it does not happen. So in pyrrole, though attack happens here, electrophilic substitution, on indole ring electrophilic substitution happens at position 3. Please remember this, okay, because this it will try not to disturb the stability of aromatic benzene ring, and then nitrogen pumps electron here, this comes here, and you get electrophilic substitution at position 3. You can see here you get a positive charge, then some base will come, will take a proton, this comes, you get here, okay. Then we'll see some other molecules. So on pyrrole, when it is attached, we saw it was indole ring. When on pyridine it is attached, benzene ring is attached, is quinoline. And when it is attached from some other position, here like position was just at the adjacent carbon, the benzene ring came. And if it is on the third carbon, on the position rather 3, I would say, when a benzene ring is attached, it is called as isoquinoline. So when a benzene is attached to pyridine on next neighboring carbon to the nitrogen, it is called quinoline. So you are having and how we give the number, we start counting from nitrogen, 1 2 3 4, then comes 5 6 7 8 9 and 10, okay. And in isoquinoline also we don't start from nitrogen, but we start from the same position. How quinoline we start counting? It is 1 2 3 4 5 6 7 8 9 and 10, okay. Now if you do nitration, okay, if you do nitration HNO3 H2SO4, please remember this. You can draw all those structures and see for yourself, otherwise just remember the addition reaction as the electrophilic substitution reaction happens at position number 5. Why it does not happen on pyridine ring? In pyrrole, it did not touch benzene ring. Everything happened in the pyrrole ring itself. But pyridine, you can see that electrophilic substitution is not happening on this ring. It is happening on benzene ring. Because we have talked about it previously, here the nitrogen lone pair is not involved in conjugation. So nitrogen, all it does is it shows minus I effect and deactivates the ring. There nitrogen was showing plus R effect and activates the ring. Here nitrogen is showing minus I effect and deactivating the ring. So electrophilic substitution reaction does not happen on pyridine ring, it happens on the benzene ring. So when you do nitration, you are getting 50% product nitration at position number 5 and 42% at position number 8. So almost you can say 50-50%. Okay, but in isoquinoline we do nitration. Nitration one kind of electrophilic substitution reaction. Other electrophilic substitution reaction like bromination, Friedel-Crafts alkylation, Friedel-Crafts acylation, everything will happen similar way. So in isoquinoline when you do nitration, you get nitration at position number 5. Okay, so remember this. On quinoline 5 and 8, on isoquinoline it happens at position number 5. Right. Next is very important topic. It is aromatic heterocyclic cycle synthesis. So synthesis we have to know. So I am giving a very little bit of how to think how we do synthesis, but it's more examination point of view. You have to just know the steps. Okay. So first thing is, now when you draw synthesis, you should know making carbon-carbon bond is quite tough. But making carbon-oxygen bond, carbon-nitrogen bond, carbon-sulfur bond, all this hetero bond making is much easier. Okay. Second point is intramolecular reaction. If within the reaction, if within the molecule if some reaction is happening, it is much faster than another molecule attacking. So intramolecular reaction is faster than intermolecule, and then 5 and 6 member rings formation is very easy. 4 member ring does not form. 3 member ring, it forms very fast. Kinetically is very favorable, but it is not stable. But 5 and 6 member is both kinetically and thermodynamically favored. That means it happens fast also, and after formation it remains stable. And then last point is aromatic molecules are very stable. So thermodynamics drive this reaction. You will see suddenly how all this is forming. What drives is the stability of the product, because whenever it is aromatic it is very, very stable. We'll see something like this molecule. If we see this is pyrrole. So pyrrole is nothing but enamine. How will you think about how to go about the reaction? So it says when you see a double bond, now mostly dehydration would have happened. Mostly. So we are showing this arrow. Okay, this is just to understand how to think about starting a formation synthesis of a large molecule. To start thinking, you have to go backward direction. Backward direction means what should I do from big to make small, 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 so that I go. You cannot see a big molecule and think from front that I start from this small molecule and then I'll make big, 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 big. Okay, so you have to always break it. So this arrow is called as retrosynthetic analysis. Retrosynthesis means from big I am making smaller, smaller, smaller. So when normal arrow means I am synthesizing, here means I am breaking. So you can see a double bond is there. So best is double bond means dehydration would have happened. So I can think of molecule where OH has been there, then H was there, and then you think about breaking this up. So when you break it up, you get R2NH because amines are formed, and this you can imagine that this is going and attacking and this will be leaving. So you get a double bond. That's how you can think about it. So let's think, if I have to make pyrrole, what we can think. So again, same way actually you can think about it. Here water will be added, all this will happen. So first you think about breaking up this. So when you break, you have NH2, you are having C double bond O, and then when you further break this also, you'll get another C double bond O, and you are having ammonia. So exactly that's how they synthesize. So they take 1,4-Dye ketone and they put ammonia, just stir it and you get a reaction. Now if you see, it's very easy to understand. Okay, just think about what is happening. H2O is lost, you get a double bond imine, and then nitrogen goes and attacks and this leaves out as water. In that process, this double bond is coming. Why all that double bond is coming? Because molecule is aromatic. Aromaticity derives. So these are very famous questions. Always they ask and very simple to get. Okay. So whenever you see something like this, put ammonia, you'll get amine. You'll get pyrrole. Understand? If you want, I will try writing the mechanism for you. Something like this it will happen. Okay. Like that is there. Imagine you are putting ammonia. See this mechanism, they are taken for granted that you will be knowing all this. Okay, so this will go and attack here, this comes here and it will take away one proton, and then again it will attack and this low H2O will be lost. Basically what you will get is double bond NH. Okay, now nitrogen has 3 bonds and water is lost. Okay, and water is lost. Then what happen after that? Now this will go and attack here. this will come here, and then like that it will happen, it will come here, like that will happen, then finally pyrrole formation happens. So 1,4 diketone ammonia, it give you this product. Similarly, if you take 1,4 diketone and just put acid little bit H plus, so H plus you can understand it will form OH plus, and then this will go and attack and water will leave, and then again aromatization happen. What you get is furan. Okay, what you get is furan. And so remember, 1,4 diketone put ammonia, you get pyrrole. 1,4 diketone you put acid, you get furan. And 1,4 diketone you put P2S5, it goes through double bond S, and you get thiophene. So these are very, very important reactions. It is always seen in all the competitive examination. Very easy to score marks, right? Now this is what part of the is in the syllabus, and this name is important. So whenever name is there, I always told you, named reactions never fail. Named reactions never change. So whenever named reaction is there, you need mechanism also. So Hans pyridine synthesis. So he was the first guy who synthesized pyridine in the lab. So you can see he didn't synthesize pure pyridine. He synthesized substituted pyridine, but it was first synthesis and quite well synthesized. So how he thought about it? He said, in pyridine let us put some R, COET, this, break it up. So when you break it up, of course, when you see this, when you break, you can think about C double bond O. You break here also, you think C double bond O, and here you'll get ammonia, same like what we thought about previously, right? Then it says you break this also and break this also. So here you'll get aldehyde, and here you break and you'll get this part. That's what, and just now what we saw the analysis, exactly same way he also thought, and he did same way, okay? So he broke up here, so you get ammonia in this place, and you get double bond O, you get double bond O, COET, here you break up, so CHO, you get aldehyde, and you get this part. Then he used these two, and he put ammonia, okay? Sorry, here I forgot to write ammonia. He put ammonia also, and at pH 8.5, that means little basic media, because of ammonia it will become basic, and in ethanol he just stirred it, and you got this molecule exactly how we thought about it, synthesized, and he oxidized, and oxidation loss of hydrogen, and hydrogen loss was there, aromatization happened. So this is important from examination point of view, okay? Let us see mechanism. So we start with this molecule. So COET is there, CH2, C double bond O, CH3. In basic conditions, what will happen? So in basic conditions, whenever there is a ketone, it undergoes enol kind of thing. It's not enol actually, it's enone. Right. So what happens is, if it was acidic condition, what you would have got is just a double bond here and OH. In basic condition, you get double bond here and O minus. It's like this. It's not exactly like this, but it's kind of equilibrium. What happens is, a base is there. Base will go and attack this, and this will come here, and this will come here. Okay, something like this happens, and that's how you get double bond here minus. But understand, it's still in equilibrium. It's not that 100% is happening. 5% or 1 or 2% molecule will go like this, but this, even if one molecule happens, this reaction will push forward the mechanism. If molecule is in this way, reaction will not move ahead. So even in 100 molecules, imagine one molecule undergoes like this. This is what will push forward. So as soon as this is consumed, another molecule will undergo such a tautomerization, and you get this, and then again happens, right? So you are getting enol ion, and then you get negative charge here. This attacks on another ketone, and then what you get is double bond here, O minus, and then of course, and then this double bond is there again. In basic condition, it comes here like this. You get a negative charge, and this is basically O minus, which is taking this proton. You appreciate what has happened. This O minus has taken this proton. This has come here, and this one comes here. Okay, and you get like this, and then this comes here, and this one will go attack here. This water comes out here, and you get this synthesized, and then you take another molecule starting from here, and this attacks here, and you get here, and you basically get this molecule, and You understand? This is again enol. So enol will tautomerize. I should rather draw this one. When tautomerization, you should always show equilibrium. You get a ketonic form. So this will be more. This will be 99%. This will be 1%. And then you put ammonia. So ammonia is H2O loss will be there. You first imine forms, and then nitrogen goes and attacks here. You get here. You oxidize and you get this. Okay. So this mechanism is important. They can ask you. They'll give you all the molecules, reactants, and they'll tell you how do you synthesize this. So the mechanism, right? Now other synthesis of pyridines. Another one is you again take 1,4 diketone. 1 2 3 4 5 1,5 diketone you take, and you react with hydroxylamine NH2OH. So NH2OH, whenever you see this, no, very interesting. As soon as you see like this NH2, understand H2O will be lost. So, and you get H2O, you get imine here, and then nitrogen attacks here, and you get this bond, and then in acidic medium, this comes here. Oxidation, basically oxidation is happening, and you are getting this pyridine. Okay. So again, we are starting with here we are starting with 1,5 diketone, react with hydroxylamine, and you get this product. Then synthesis of diketones by Mannich reaction. Right, so here you are having a cyclohexanone. Yeah, so it's saying how do you come to this diketone formation? It says you take something like simple cyclohexanone, and then it's telling how do you do by Mannich reaction. Mannich reaction, if you remember, we add HCHO and we remove water and all. This is very simple actually. It's like in acidic condition, it will have enol. This will go on attack, and this will attack here, this will leave, and you get this kind of molecule, right? That's what they're showing in retrosynthesis also. Then another synthesis, there you have ketone, you react with ethyl formate, right? It's a ester, so ethyl formate or ethyl methanoate, you can say. Formate will be a common name, IUPAC name will be ethyl methanoate. Then in presence of base, you get negative charge here, this will attack here, and you get like this molecule. Then you react with another CN, and then this will go and attack. You can see this this part. Okay, so this part, this is there, this reacts with this, and this basically takes a proton. You're getting negative, you get O minus. I hope you understand what I'm saying. What I'm saying is this one comes here, this will go and take away proton from here, then this comes here, you get minus charge here. That's all. Okay, and then you have this molecule, and then this undergoes a reaction. So all these are very simple. This will come and attack here, this will go and attack here, and this will take away proton from the medium, and that's how you get this molecule. This also maybe I should show you. Okay, so what is happening here is the proton is there, here proton is there. So this negative charge comes and attacks here. So this will come here on this carbon, and this will take away this proton. Okay, and this proton will come here, and you come here, and you get this molecule, right? And then you are having this molecule NH2CN, which will again synthesize. When you see such like this, you just catch it up. H2O will be lost, double bond N, and then aromatization happens. This comes here, you're getting this, and finally aromatization happens, water loss, and then you get this molecule. Okay, next is another very important reaction. It is called as Fischer-Indol synthesis. Now Fischer-Indol synthesis is very, very important. Okay, so we know indol is pyrrole fused with a benzene. So you start with phenyl hydrazine. This is very important. Okay, I have seen this 100 places, all completed examination. You take phenyl hydrazine, react with cyclohexanone. So first thing what happens, actually this will go and H2O is lost, and then this attack happen, lot of things happen, we'll see the mechanism, and then you get this. So this is substituted Fischer-Indol because this is a benzene ring, and then you are having pyrrole ring on it, and there is a substitution of alkyl group, cycloalkyl group here. So how the reaction happens? So you react first with phenyl hydrazine. Hydrazine, you know, is always NH2. You attach a benzene ring, it is called as phenyl hydrazine. You react with cyclohexanone, and water loss is there, you get a double bond here. Okay, they take it for granted that you know this much. They don't show mechanism because now you have grown up, but you should know basically it's a very simple thing. It will always be like this. It will go and attack here, this will come up and take away proton, then again it will attack and take away another proton and water is lost and you get double bond like this. Okay, so this is taken for granted. Whenever you see this, you don't need to show the mechanism. Immediately water loss and you get hydrazone. This is called as hydrazone. So cyclohexanone phenyl hydrazone. And then this is 3,3 sigmatropic shift. Okay, so this will be studying separately pericyclic reaction, but basically wherever the bond is breaking, no, you have to start counting from both sides. You can see here the bond is breaking, so you start counting from here. 1, 2 and 3. Here also bond is breaking, so start counting from here. So 1, 2 and 3. And where the bond formation is happening, it's happening here. So it is called as 3,3 sigmatropic shift. It is very favorable. Just in little bit you heat it, this reaction happens. So N bond breaks, this comes here, this goes and attacks here, this comes here, and you get double bond here, and you get this. Okay, I did not show this, but all these are very simple. You can see from here, no, it has come here to get this molecule. Okay, all these are very important. You have to practice. Okay, directly question will be given. Show the synthesis of this molecule using Fischer-Indole synthesis. So you start with your phenylhydrazine, react with cyclohexanone, you get this, and then you show like this, and then you show 3,3 sigmatropic shift. 3,3 sigmatropic shift is very easy. You have to just practice. Okay, tuck, it comes here, this goes and attacks here, this goes and attacks here, and you get double bond like this, and then it becomes simple. This comes here, you get NH2, and then NH2 will go and attack here. You can see all this expected. It forms bond here, this ammonia is lost, and then aromaticity will be gained like that, and you get this. Okay, synthesis of that was synthesis of Fischer-Indole synthesis. Okay, now we also studied about quinoline. So quinoline synthesis is let us see retrosynthesis. So here again you can see this nitrogen is there. So basically it will be breaking up like this mostly, and you get here NH2 and you get double bond O here. Then once you get this, you can start breaking it up. Then when you break up, you are having a ketonic group, and then here, and things like that. Okay, same way here also. So let us see the synthesis part. So synthesis is, again you start with something like this only is there. So you start with aniline and you react with ketones, diketone 1,3 diketone. Okay, here also we saw it was 1,3 diketone. So you react with diketone. So straight away when you see H2O, double bond O and NH2, water loss. Okay, you get imine, and then it will it's an equilibrium. So basically this hydrogen is taken away, this comes here, this comes here, and you get NH, you get double bond here, and then nitrogen lone pair attacks here, this attacks here, and you're getting this, and you're having positive charge of nitrogen. Then this comes here, this comes here. Okay, and last step is left. So last step is again because aromaticity has to be gained, so this hydrogen is taken away, and this comes here, water loss, and you get pyridine. Okay, this finishes the heterocyclic compounds. Okay, thank you.